In this video, we're going to recall some of the main theorems we've seen in Calc 1, recall maybe some pictures as to what these theorems are saying, and then talk about a new theorem which is going to play a major role when it comes to proving the fundamental theorem of calculus. So, first I want to start with the intermediate value theorem. The intermediate value theorem says that if f is continuous on the closed interval ab, and y is between f of a and f of b, then there is some c between a and b such that f of c equals y. What does this mean? Well, let's say I have some continuous function that looks like this. Well, we'll have a, we'll have b, and let's say I have a function that looks like this. Well, I can draw these lines to f of a and f of b. And what this is saying is if I choose some y between f of a and f of b, I should be able to find a point between a and b where f of that point equals y. So in this case, I look at my line, I cut across to see where does the function hit that value. It hits it right here. And then I see what coordinate do I hit. We'll call that c. And what it's saying is I'll always be able to find a c between a and b such that, again, f of c is y, with y being between f of a and f of b. That's kind of our picture for the intermediate value theorem. What the extreme value theorem says is that if f is continuous on the closed interval ab, then f attains a global maximum and a global minimum on that interval. So let's use a similar picture. So we'll have a and b here. We'll have the same function f. And this picture will be kind of brief. I just ask myself, does this have a global minimum and a global maximum? The answer is yes, and they're kind of boring. I have a global min. Actually, I'll do this in red. I have a global minimum at this endpoint and a global maximum at that endpoint. Now, of course, we don't always have our global max or global min at the endpoints. We could have a different picture, maybe something like this. Where our global max is still at an endpoint, but our global min is right here. But what we're saying is if we're on a closed interval and we have a function on that interval, yes, we'll always be able to find a global max and a global min. Lastly, we'll talk about the mean value theorem. The mean value theorem says that if f is continuous on a closed interval ab and differentiable on the open interval ab, then there is some c between a and b such that the derivative at c equals f of b minus f of a over b minus a. And our picture here will have the same kind of function as we were using before. And I'll try to make sure this looks differentiable. What we're getting is we have some tangent line, or we have some secant line between A and B, which will look something like this. And what we're saying is that there's some C, we'll say maybe here's a good candidate for that, between A and B, where the tangent line at C is parallel to the secant line from A to B. That's kind of our picture there. I'm going to give it one more shot to make that line nice and straight and passing through there. That's slightly better. Okay. So that's what this is saying, is I can find a point C where the tangent line at C is parallel to the secant line from f of a to f of b. So that's the mean value theorem. And now we're going to talk about a new mean value theorem, the mean value theorem for integrals. Let f be continuous on a, b, then there's some c between a and b such that f of c equals the integral from a to b of f of x dx divided by b minus a or f of c times b minus a equals the integral from a to b of f of x dx. So what does this look like? Well, let's say I have a graph. We'll do the same graph that we've been doing in all these other pictures. And let's say we had this picture here. So I'm going to do some shading in some different colors. If I'm looking at the integral from a to b of f of x dx, it's going to be this area here. Now, I shaded this blue for a reason, because I want to think of this as kind of like a fish tank full of water here, going from A and B. And you could imagine that this fish tank has some ripples in it, but if you were to let the ripples even out over time, they might settle to some new position in like a more flat surface, and that flat surface might look more like this box. Just as a guess. That may or may not be accurate. That's actually probably a little low. So we're saying that, actually, that is a little low. Let's try again. Maybe more like this box. And what we're saying is that if you were to kind of let the waves level out, they would fill in this fish tank. And we call this value here, this new level once the waves level out, this is going to be, well, we're saying this has the same area as the original thing, but it has so let's look at the areas of both of these things. This has an area, obviously, of the integral from a to b of f of x dx. If I call this point, I'll call this average, then we would say that this has it's, the area of this new box with a flat top, that's given by this average value times b minus a. It's just a rectangle with a height of average and a base of b minus a. And we call this thing the average value, and if you do a little bit of arithmetic, you will see that average equals the integral from a to b of f of x dx divided by b minus a. Because we're saying these things have the same area, so they have to be equal. Okay. And what the mean value theorem is saying is similar to some things that we've seen before. There has to be some point where f equals that average value, and that has to happen somewhere between a and b. So we're saying that at this point c, f of c equals the integral, it equals that average value, which is the integral of ab of f of x dx divided by b minus a. So that's what the mean value theorem is saying for integrals. And I'm going to give myself a little bit more space here. Why do we call this the mean value theorem? Well, let me go ahead and replace, let's think of, instead of thinking of f of x, I'm going to consider r of x, which is going to be the derivative of some other function f of x. So I'm using r to stand for maybe like rate. Then the mean value theorem for integrals tells me that r of c, there's some c between a and b, such that r of c equals the integral from a to b of r of x dx over b minus a. But the fundamental theorem of calculus tells me that this right-hand side is going to be an antiderivative of r. Well, I know that an antiderivative of r is going to be f, because f's the antiderivative, or f is the derivative of r. So we'll use that antiderivative, f of b minus f of a over b minus a. And what more do we know? Well, we said that r is just the derivative of, or r is equal to the derivative of f. So if we replace r of c with f prime of c, we get that f prime of c equals f of b minus f of a over b minus a, which is exactly the equality that we get in the mean value theorem for derivatives. So we see that these are actually pretty closely linked together. So that is the mean value theorem for integrals.